we present NeurOx, Neural Knox Supervision for Monocular 3D Object Localization. In this work, we study Knox-based method for localizing cars in autonomous driving. The Knox-based methods predict normalized object coordinate maps or Knox maps that gives 2D 3D correspondences, which forms a PNP problem for solving the object poses. However, for autonomous driving, the lacking for high-quality shape supervisions limits the performance of the Knox-based methods. The LiDAR or densified LiDAR provides sparse and noisy shape supervisions, leads to suboptimal performance. In this work, we propose a new method for providing high-quality Knox supervisions. Our motivation is to replace the LiDAR supervision with a nerve that deforms in a low-rank space that benefits from learning a shape prior from the whole dataset. And this video will first introduce our proposed low-rank nerve representation, followed up with a few important implementation details. Our low-rank deformable nerve is built upon a grid-based nerve representation, and specifically we define several latent grids, with one of them representing the average shape and others defining the deformations. And the number of deformation bases is said to be much smaller than the number of training samples to enforce the low-rank constraint. And by fusing these grids with image-conditioned deformation coefficients, we can place the latent cars on the map with ground truth object extents. And after decoding and volume rendering, we can obtain very nice and clean Knox maps to supervise the training. To train the nerve, we apply three losses. The main loss is the mask loss that enforces the silhouette consistency, and an RGB loss is also applied to provide additional photometric constraints, and our system works very well with only these two losses. But with an optional LiDAR loss, it can also achieve a slightly better performance. And next, we discuss a few important implementation details. The first is deformation regularization. While without any constraints, we observe large deformation coefficients, creating unnecessary deformations resulting in noisy shapes. So we use a KL divergence loss to regularize the deformation coefficients, same as the one used in variational autoencoders. This loss minimizes the information gained from the deformation coefficients to suppress unnecessary deformations, and as a result, the shape becomes much cleaner. The second detail is regarding the visual hole ambiguity that occurs while not using the LiDAR loss. And as I illustrated, the visual hole ambiguity happens to the green and orange shape who has the same silhouette for the two cameras. And in our case, the back of the car is squeezed in due to this ambiguity. So to suppress such random effect during our training, we add a dense prior to encourage filling the ambiguous regions. The final detail is an important network design choice between the scene-centric and object-centric view. The scene-centric and object-centric strategies differs in either cropping the object from the feature maps or from the RGB images. The scene-centric view certainly provides richer context information. However, we found such context information inject biases that degenerates the Knox map prediction task. So we choose to use object-centric views that clips away the context information to enforce the network learning a strict mapping from the object appearance to the Knox. And in this way, we achieve a significant improvement, especially for distant and occluded objects. Here, we visualize different Knox supervisions with their predictions. The noise in sparse LiDAR and the LiDAR completions are reflected in their final Knox predictions, while on the other hand, our method only using masks already gives a very good shape, results in good Knox predictions. And by further adding the LiDAR loss, both the supervision and predictions obtained more details. We tested the localization performance on the KITTI benchmark, and compared to existing Knox methods that trained using LiDAR or external CAD models, our method using NeurOx supervisions achieved a significant improvement, even without using LiDAR supervisions. I want to thank you for watching this video, and please visit our paper for more details.